Do you know the absolute fatal mistake student pilots make when mixing hydraulic fluids? You know, it's a classic ATPL exam trap. And doing it in real life could actually lead to a complete system failure. Have you ever seen this mistake before?
Welcome to BIS Explainer. Today, we're going to take the headache out of aircraft electrical systems, generators, buses, and hydraulic circuits so you can absolutely crush those ATPL systems questions. If you're preparing for your exams and want to understand the underlying logic without all the confusion, this lesson is going to seriously strengthen your technical foundation.
Okay, let's dive right into this. We'll start with the ATPL systems trap, then move on to electrical power and distribution, electrical failures and protections, hydraulic fluids and properties, hydraulic pumps and components, and finally, we'll wrap up with a quick summary and some key exam tips.
All right, Part 1, the ATPL Systems Trap and Understanding Redundancy.
You see, aircraft systems questions don't just test rote memorization, they heavily test your logical understanding of redundancy and failure scenarios. Why does this actually matter in real flight? Well, when things go wrong up there, you need to know exactly how the aircraft is going to react. Most metal aircraft use a single wire system. The airframe itself actually acts as the return path, and all metal components are electrically bonded to maintain equal potential, which prevents dangerous sparking. But if you're flying an aircraft made of non-conductive composite materials, like a diamond star, you need a double pull system. That just means two wires, one taking the current out and another bringing it back. Oh, and here's an interesting fact. Friction from air molecules builds up static charge during flight. That's exactly why we use static wicks on the trailing edges. They provide a controlled discharge into the atmosphere, which critically prevents severe radio interference from messing with your communications.
Moving on to Part 2, electrical power and distribution, specifically alternators versus generators. Now, what's really interesting here is how power is actually created on board. Alternators and generators fundamentally do the exact same core job, right? They produce the electricity needed to charge your battery and run your equipment, but here is the crucial difference for your exams. A generator produces direct current, or DC, right out of the gate. An alternator, on the other hand, produces alternating current, or AC, internally. It then uses a built-in device called a diode rectifier to convert that AC into DC before it finally hits the aircraft's main bus bar.
But what about large transport aircraft that are actually running on AC power? Well, we basically have two main types of systems. First, frequency-wild systems. These are used in smaller aircraft where the generator's RPM directly dictates the AC frequency. It's a simple setup and it's great for basic resistive loads like window heaters or de-icing boots. However, modern transport aircraft need constant frequency systems. They have to keep that AC frequency strictly locked at 400 Hz. They do this using a constant speed drive unit, or more commonly nowadays, an integrated drive generator, an IDG. This keeps the frequency perfectly steady regardless of what the engine RPM is doing during your climb, cruise, or descent. Because of those super strict frequency rules, plugging an aircraft into external AC power on the ramp requires some exact conditions. Before that external power cart can even energize the aircraft, four parameters absolutely must be perfectly aligned. Correct voltage, correct frequency, correct phase sequence, and a dead bus, which just means no other power source is currently feeding it. A phase order mismatch, that means immediate refusal by the aircraft's electrical system, which keeps your onboard electronics completely safe from reversed phases. Okay, Part 3, electrical failures and protections, keeping the lights on. So what would you actually do in a failure situation? To figure that out, we need to look at how the aircraft actively protects itself from electrical fires and shorts. There are two essential components you've got to remember here, the GCB and the DPC. The generator circuit breaker, or GCB, connects the generator to its bus. Now, don't let the name trick you, it's actually a heavy-duty contactor, not just a standard little circuit breaker protecting a single wire. Then we have the differential protection circuit, the DPC. Think of this guy as a security guard. It constantly compares the outgoing current against the returning current. If there is a difference, it detects a leak and will instantly isolate that fault. So the absolutely crucial point here for your single-engine operations is this. If your only alternator or generator fails mid-flight, you are going to see a constant, heavy discharge on your ammeter. The golden rule? Shed the load. Reduce your electrical loads to an absolute minimum and land as soon as practicable. You are now entirely reliant on a rapidly depleting battery to keep your engine ignition, radios, and instruments alive. No pressure, right?
All right, moving on to Section 4, hydraulic fluids and properties, the physical muscle.
We're leaving the electrical wires behind now and diving into hydraulics.
hydraulics rely on an incompressible fluid to translate a really small physical effort into massive mechanical force, like actuating flight controls or dropping heavy landing gear. But to really grasp the system, you need to know your fluids. On one side, we've got mineral-based fluids, which are typically dyed red. You'll see these in military aircraft and smaller turboprops because they're relatively cheap, less corrosive to paint, and offer fantastic lubrication. On the flip side, we have synthetic fluids, commonly known by the brand name Skydrol, which you'll spot because they're purple, green, or amber. This is the gold standard for commercial aviation. Why? Because Skydrol is highly fire-resistant and has a way higher temperature tolerance, which is absolutely critical for the safety of large airliners.
Which brings us right back to that question at the very beginning of this explainer. What actually happens if you mix them? Well, remember this specific mnemonic for your exam. Mix equals mess equals melt seals. These fluids have completely different chemical makeups and require entirely different types of rubber seals. So topping off a synthetic Skydrol system with red mineral fluid, it will literally melt the seals and lead to a catastrophic total system failure. Just don't do it. Let's move to part 5, hydraulic pumps and components, and see how we actually generate pressure. Let's see how this all builds into a working system that actually pressurizes these fluid lines. If you trace the path of the fluid, it starts resting in the reservoir. The pump then pulls it out and pressurizes the line. Now, if the pressure gets too high, the pressure relief valve acts as a safety outlet, bleeding off that excess pressure by sending fluid right back to the reservoir. The safely pressurized fluid then pushes into the actuating cylinder, creating that resultant physical force to move, say, your heavy landing gear.
Now, ATPL exams absolutely love testing pump types. First, we have a constant displacement pump. This moves the exact same volume of fluid with every single rotation. Because it's basically relentless, it requires an automatic cutout valve, or ACOV, to route fluid back to the reservoir when the system is already fully pressurized. Conversely, a variable displacement pump actively adjusts its internal swash plate angle. It maintains a constant pressure but with a variable flow, which completely removes the need for an ACOV. Aircraft systems also follow a super strict hierarchy when it comes to hydraulic pumps, all based on reliability and power output. The primary source is almost always engine-driven. Second in line is the PTU. Third is an electric pump, which is often used as a supplementary backup. And finally, your absolute last resort emergency source is the RAT, the ram air turbine. The RAT is last because it relies purely on your aircraft's forward airspeed to spin a little propeller, and it typically only produces enough pressure to power the absolute essential flight controls. Let's zoom in on number 2 on that list, the Power Transfer Unit, or PTU. Here is your golden memory trick for the exam. Power only, no fluid. A PTU mechanically transfers power from a healthy hydraulic system over to a failed one, without ever mixing the actual fluids between the two systems. It's essentially a hydraulic motor on one side, driving a hydraulic pump on the other. Pretty clever, right? All right, here are 2 more crucial protective components you really need to memorize. First is a hydraulic fuse. This is designed to detect excessive flow and physically shut it off, stopping fluid loss if you get a massive downstream leak, like a blown hose. Next up is the accumulator. This is pre-charged with a nitrogen gas cushion to about 1/3 of the normal system pressure. It acts kind of like a battery for hydraulics. It stores energy, dampens pressure fluctuations, and provides an emergency energy buffer. This is exactly what saves the day and lets you apply your wheel brakes even if all the main pumps completely fail.
Finally, Section 6, Summary and Exam Tips. Let's secure your knowledge. We have covered a ton of ground today, so let's lock in those key takeaways and memory tricks you're absolutely going to need to pass your ATPL Systems questions. For connecting external AC power, remember the 4 rules: correct voltage, frequency, phase, and a dead bus. If you lose your only generator in a single engine aircraft, reduce your electrical load and land ASAP. Never, ever mix your hydraulic fluids. Red means mineral, while purple, green, or amber means synthetic Skydrol. Remember, the PTU transfers mechanical power, not fluid. And your RAT, that's your air-driven emergency pump, deployed only when everything else is gone. So, are you ready to pass ATPL Aircraft Systems? When you sit down for that exam, please don't just rely on raw memorization. Trust the logic behind the systems. Think carefully about how the redundancy is specifically designed to keep the aircraft safe. And I promise, the answers will become totally clear. Mastering these concepts isn't just about passing a test. It's what builds a solid, safe technical foundation for the rest of your flying career. Next time you board an aircraft, ask yourself, if a generator fails right now, exactly which systems are keeping me safe? If you want more exam tips to help answer questions just like that, hit subscribe. Keep studying hard, trust your training, and we'll see you in the next explainer.